Okay, we'll get started. So, hello, people online. We're very lucky this week to have our very own Salford alumni, Paul Kendrick, here from Logitech, who's going to talk to us about improving video conferencing with AI.
Thank you very much. So yes, thank you for having me. It's always awesome to come back. Awesome to come back again. So, is this working? Yeah. So yes, so I work for Logitech. Specifically, you've probably heard of Logitech from the point of view, especially you got guys in here who've kind of done many subjective tests. You know exactly who we are. But if you haven't, we're famous for making these mice and keyboards. Famous for making those kind of things. I don't do anything like that. I work in a subsidiary of Logitech called Logitech for Business, and we mostly focus on what we call video collaboration. So this is we sell products mostly directly to businesses, and they kit out their meeting rooms, their conference rooms with these kind of bits of kit, which would be a video bar, like go underneath the screen at the front of the room with a camera, microphones and speakers. We also sell kind of separate microphones, cameras, interactive whiteboards, those kind of things. So that's kind of the space that I'm working in. During this talk, I'm going to give a bit of an overview of the Audio AI team, which is the team that I work with within Logitech. Try and just talk a little bit about what the problems, what are the challenges that you have when you're trying to kind of capture speech and you're trying to capture conferences within these meeting rooms, etc. What are the challenges? Give an overview of what features we are working on, what features we are developing, okay. And then a couple of demos. So these are just kind of marketing demos, but they give you an idea of what the products do. And then I wanted to do a bit of a deep dive into, we kind of ML AI is ubiquitous nowadays, but kind of one of the questions I have is how do you go from, okay, I've trained my model in Jupyter Notebook, and now it's deployed in a product. What is that transition? What are the challenges, and how do you do that? Because that's what we do. So, and then I want to go for so it's deep dive. It's not really a deep dive. Just give a bit of an overview of some of the work that I've done, which is on the ML direction of arrival algorithm. So this is an algorithm that tries to predict the direction of speech within the group. So I'm going to go through a little bit of a deep dive into the algorithm there. So we sit within Logitech for Business. We're in the audio engineering group. So Logitech itself, there's about 8,000 people who work all over the world. And within audio engineering, we can split ourselves up into the firmware team, who are responsible for kind of taking our features and actually integrating them into the product and making sure they work. We have a DSP team who basically do stuff very similar to us, and there's a lot of collaboration there. But there are things like beamformers and things like this. So DSP team. We have extensive acoustic testing, both in kind of lab conditions, and also we have teams of people who will test our products in I guess simulated environments like actual conference rooms and start using the product to make sure, like Q&A basically, make sure quality assurance, make sure these products actually work. And then there's us, Audio AI team. In particular, we also collaborate closely with the computer vision team, who we share data to try and get some of our features to work. It's multimodal, so we're using both audio and video to get these things to work. This is our team. Got somebody in charge. We have we can split ourselves up like this. We have an algorithm design team. There's basically 3 people, which I'm one of them. So these are people who design the algorithms, mostly in Python. Used to be MATLAB, but now we're so yeah, these we design and train the algorithms. We have an evaluation team based in Ukraine, who do actually the testing of our products in conference rooms. We have a person, this is interesting. We have one person dedicated to managing data. It's very useful. He's responsible for sourcing and commissioning data sets, but in particular ensuring legality. So making sure any data set that is used at any point in the training of a model that we're using is legal. We're allowed to use it. So, for instance, has anybody heard of audio set? Can't use anything trained by audio set, which is everything. so yeah, ensuring legal compliance. There's a lot of work going on in there. And then what I like to think of as the secret sauce in our team, which actually gets things done. I'm not going to say it does the proper work, but it's the embedded apps team. And these people who will take our prototype algorithms that we've designed and turn it into production code so it can actually get deployed. So they understand different ML frameworks. Just talking to Will about this kind of thing. These guys do. We've got a dedicated team of people who actually take the models and ensure they work. It's not a problem. We also have around 4 interns per year, normally based in Lausanne in Switzerland, because our office is right next to EPFL. So we take a lot of students, master's students from EPFL, who will do a 6-month project with us, and they do the interesting stuff. So they do the cutting edge research. They look to see what is the state of the art. So they're kind of like 3 years ahead of what's in the product. We're kind of looking into the future. What kind of technologies can we use and bring to our products? And they're doing risky stuff. We do publish research via interns next. So what's our problem? So they're in a meeting room. You need to be able to capture speech from wherever anybody's sat. It doesn't matter where they are, and we want the quality of the speech to be excellent, as good as it possibly can be. And the other thing that we need is we need our products to work without any user input whatsoever. So they need to turn on, go, just work, and it sounds great. That's what we need. And kind of this image, obviously, ChatGPT generated image, is just trying to kind of emphasize. We've got a team of people who are all editing the video and the audio and capturing different aspects, knowing what to tune into. This is the problem we're trying to solve. But meeting rooms can often have terrible acoustics. Particularly, you may have, I know you guys have this problem with certain rooms where you can just hear the lecture next door. So you may have poor sound insulation from neighbouring rooms. Another challenge for meeting rooms is that loads of people like to build glass walls. I wish they wouldn't, but yeah, build a glass wall, very highly reflective surface. You're going to get problematic early reflections, reverberation. You can't attach mics to people. People just want to sit down and have a meeting and want it to just work. So all of this needs to be done at distance. And people may be eating crisps or drinking cans of Coke or falafel. Yeah, making a noise, or John, this is your moment. Thank you. There you go. People might be kind of making these kind of noises, and you don't want to transmit these. These need to be kind of filtered out. The other one is a conference is a multi-way conversation. You've got everybody in the room, but then you're going to have somebody on the far end, or many people on the far end. So you're going to have a loudspeaker in the room that is projecting that sound from the person talking as well. So the loudspeakers need to be quite loud. Got a large room, it's quite loud. And our devices are kind of all in one. You've got a camera, you've got a speaker, you've got a microphone. So you have a double problem, which is people are a long distance away, so the sound is relatively quiet at the microphones, and you've got a loudspeaker that's incredibly loud, and of course that loudspeaker gets picked up on the microphone. So you can't transmit that because you end up with this feedback back. So we need to be able to suppress these, and that's a particularly difficult problem. You may have people talking over each other, and as I mentioned before, open spaces is another particular challenge. If you've got lots of babble noise in the background, high levels of background noise and things like this. So that's the problem. We don't have anybody who can direct the cameras and basically you know, who do you want to frame at any moment in time? It's fine if you're giving a lecture, the camera's pointing at me, but as mentioned before, if we have a question and I need to repeat it, wouldn't it be great if just the camera focused on the person doing the question and it got picked up? So that's the problem that we're trying to solve. Nobody's directing the cameras. We've got multiple microphones around the room, perhaps. There might be one microphone that's better at picking up one person than another. You need to make that choice. And yeah, you don't know how much compression to apply. You don't know what EQ might be best. Nobody's doing this. So the point is that all of this must be fully automated, and even more difficult, it must happen at the edge. It must happen on the product before it gets transmitted. That's the problem. And in terms of the solutions, these are a couple of examples of products that we make. So they call these video bars. They have built-in camera, microphone, microphone. In terms of the features that we work on, these are sort of the main highlights of the things that we work on. There's some other things as well, but these are the main ones. We work on denoising algorithms to remove John's crisp packet noises, de-reverb, try and remove echoes and reverberation, and just make the speech sound more direct. You know, that's it is quite impressive how well modern de-reverbs work. Consistent speech level, you've got and then talking loudly, need some sort of automatic gain control, and then direction of speech. So you need to know who's talking and when they're talking, so that you can point the camera at them, focus on them, or you can select the correct microphone or point the beamformer in the correct direction. And this is the area that I'm working on, direction of speech. And all this stuff kind of feeds and drives a number of other features. So, like I said, we can use the direction of speech to steer the audio beam, and also it unlocks a number of these audio-visual features. So these are features that are not developed by our team. These are features developed by the computer vision team. We call it Right Sight, and they do all sorts of really cool, clever things. So speaker tracking, so you can focus on the person who's talking, and these other ones as well. I'll just give you a quick demo of what that actually means. So here's it's a marketing video, but you get the idea of what we're trying to do. So this is the framing of the talker, which is driven by the direction of speech, which is the algorithm that our team developed. The music's better in the other one. So that's speaker view, direction of speech. So it's using the direction of speech algorithm. It's going what angle and is somebody actively talking. That's the kind of the data that we're passing to the computer vision team to be able to do that. The next one is called Logitech Sight. This is the sort of first product I worked on when I joined Logitech in 2022, and this is got an AI-powered camera. So it's got two cameras. It's not quite 360 degrees, but almost. Basically, the idea is the blind spot that you point towards the screen where nobody's sat anywhere. So you put it in the middle of a table, and you can capture a meeting around a table much better than you could if you had like a camera on the wall. And I think it's pretty cool. Anyway, this is an example. disappear. Okay, that's it. So that's the idea. You can see. I think it's kind of a game changer for these kind of meetings where you stick one of these devices in the middle. Normally, you just have a long view down of a boardroom or something, and you know you don't really feel involved because nobody's looking at you. They're looking at each other and having a conversation. But all of a sudden, you stick this thing in the middle, and it chops you up like you would do on a Zoom call, like you would be at home. So. And that's all driven by the direction of arrival. So it's going somebody in that direction, they are actively speaking, and then the vision team use that to make a decision to frame that person. So yeah, it's pretty cool. So when I first joined 2022, that product wasn't released yet, and this was the first sort of product that we were working on. It was kind of the test bed for this feature. We were using a DSP-based direction of arrival solution, and it had some problems. It tended to point at the loudest sound, which could have been John's crisp packet or whatever. And also it had some issues where if there were two people talking at the same time, it tended to point in the middle. Not great. So the result was the beamformer would point at noises and not at the people who were talking, so the sound quality was poor. And those features that I just showed wouldn't work. So there needed to be a solution. So we were tasked with coming up with a solution. So the first question is, how can you got some sort of cool new ML feature, how do you go around deploying it? So how do we do this? So this could be the sequence that we go through, right? Download the latest paper, what's the cutting edge research? Brilliant. Implement it in the Jupyter notebook, flash. Download the data sets. Hopefully somebody's uploaded and stored on Figshare or whatever. Figshare is still a thing. Train the model and then find the big red button that says deploy, press it. I couldn't find that button. So this isn't what happened. I've been enjoying generating images. So this is the more likely scenario of what happens. Clearly, there's lots more things that need to happen. There's many more challenges. We've got challenges with data. So the real world data that you were recording most likely does not match that data set that you've downloaded. You're going to have some sort of data drift between them. Might be poor quality. You might not have enough. And importantly for us, is it legal? And actually, we find that a lot of the data sets that we would like to use simply we just can't because it doesn't tick all of the boxes for the regulations. Some model limitations. Some models are going to struggle with edge cases. There's almost zero chance that that the model that you've implemented was designed exactly for the scenario you're trying to deploy it in. So you might struggle with generalization, integration issues. So we were chatting about this before. You may have a model with loads of different transformer layers and things like this, and lots of dynamic things going on in the model. You can't deploy because basically the deployment framework that you're using probably isn't going to support the layer types that you're implementing. So you need to think about this from the offset. Monitoring needs. This is interesting. So explaining what's going on with ML and AI is difficult. It's they're black boxes. You've got to understand, why is my system failing? It's hard. And once you take that black box and stick it in a live situation in a product and sell it to people, it's even harder. So trying to figure out the monitoring needs, what do you need to collect? How can you understand when things are going wrong? So a lot of our time is spent building diagnostic tools to try and understand what's going wrong with our product. And high complexity. A lot of the time, you implement this system, you've got loads of memory, but you need to think about actually what it's going to be deployed on. This model was developed on a laptop with lots of memory. Actually, it's getting deployed on the edge with a lot less. So a lot of projects fail because of complexity and not having well-defined requirements at the start. So I thought it'd be interesting just to talk briefly about machine learning technology readiness levels, ML TRLs. So hands up, who's heard of technology readiness levels? Excellent. So this is something we've been thinking about for a while, because we're trying to think of, how do we make this process of deploying ML systems easier and better? And this is kind of one of the tools that we use. So they're based on technology readiness levels, and these were basically readiness levels. How ready is a technology for deployment? And they were developed by NASA in the 70s to do with the space program. What's the chances of your rocket exploding? Obviously, more important, what are the chances that you can't hear somebody? But yeah, it's the same kind of thing. So it assesses the maturity of products. And this is from a recent publication, 2022, by some kind of clever people here. So it seems like quite a nice way for assessing how well our ML system, how ready it is for deployment. Because we want to assure it's robust, it's reliable, and that we can scale this before it actually put it into operational use. And the thing that's quite interesting for us is Logitech's a big organization with lots of different teams who have their own priorities and understanding of the world, their own worldview. And it's developing a common language so people know, all right, this is ready to go. You can talk to people from different departments and you know what we're talking about. So if you're interested, I suggest you have a look at the article. It's quite a good one. I'm not going to spend too long on it, but I just thought it would be good to give this in context. And the other thing I wanted to do was to try and ask about whether this has any validity in academic research as well. It may not, but have a think about that when I talk through it. How ready is this work for publication? I remember thinking back working with Trevor. We worked on a sound quality project, and we were trying to get people to use our technology, and it was quite a struggle. And I wonder if thinking about it in this kind of way might help that. It's getting people to adopt the technology. So for first principles, we're talking literature review, whiteboarding ideas, very basic kind of stuff. And the idea with these TRLs is the sort of gated criteria that you have to pass to go on to the next level. But once you pass these criteria, you can say that your technology is going up in level. So the next one would be goal-orientated research. So this is low-level hacky experiments, Jupyter notebooks, all that kind of thing. Very quick and dirty experiments, kind of exploratory research to try and define the problem space a little bit better. Moving on to the next one would be proof of principle. So this would be you develop some kind of simulation test beds to evaluate your algorithm. And probably the most important thing I think here is that you define your requirements. What your product requirements? What do you want this thing to do? You write big documents in this exactly what you want this thing to do. That's probably one of the most important things. Next up, systems development, and then that's kind of when you shift over from your hacky prototyping code to something that's a little bit more solid, and you start trying to develop frameworks for testing things. So like DOA would be, okay, I've developed a simulation environment of a geometric simulation of a microphone array in a room. I can test it using that. Proof of concept would be then when you start using real data that you can say, yeah, this is starting to work. It's coming together. We know if it works on this data set. We've got something that can work. And then we get to machine learning capability. So that's kind of when you transition from your model trained on your laptop to putting the framework around it to get it to work. It's kind of machine learning capability. And this is an interesting one here. So this is where you start to get shared ownership, where maybe both the research and development team and the product team start collaborating to try and actually start producing the product. And this going from 5 to 6 is hard. So we'd often call this the valley of death. Sounds a bit ominous, but yeah, actually graduating from something that you've sort of demonstrated to be capable, you then need to get buy-in from basically the people called the purse strings. This is often where ML projects start to fail. You get this far, demonstrate capability, but now somebody has to assign a check. Somebody has to assign resources. So it's at this point where a lot of kind of ML projects start to fail. You need some resources to ramp things up. Assuming you get past that, you then start application development. So this is your writing your production code. You integrate it into your product. And then the last stage, level 8, mission ready. Everything's together. You've got a prototype product. You can go and put it in some rooms and go and test it, and make sure it works. And you can always go back, and we go back many times. Oh, it doesn't work in this room. It's too reverberant. It's failing. It doesn't work on these type of noises. Repeat. So this is the kind of thing. And then deployment. So deployment, you're mostly focusing on monitoring how well the product's working in the field. So then you can kind of diagnose faults and improve it and iterate again. So that's, I won't say when I developed the MLDOA we used this, because we didn't, but I can see a lot of kind of similarities with how we progressed. And we're thinking that this is a great tool for us as a sort of company to use, so we can kind of communicate with other teams going, right, I've made this bit, this is ready, this is TRL5, you now need to do this bit, and then management can say, oh yeah, no, they've done this bit, and they can basically poke a finger and get them to do it. So we're experimenting with using this framework. Right, back to direction of speech prediction, MLDOA. So this is the project I started working on so the first thing, day one, they asked me to do some work on MLDOA, specifically for that Logitech Sight camera device, which it's got a 6 microphone, well, it's a 7 microphone array, one in the middle, so a circular array with one in the middle. I'm trying to get the direction of speech from that. So I've just kind of indicated what technology readiness level we're at. That's like a sort of go through the history process of how we develop this feature. Of course, the first step was literature review. So find out what are the possible solutions, and then try them out. Quick, dirty simulations. So we use Pyrum acoustics. If people are familiar with Pyrum acoustics, it has its limitations, but it's great for kind of quick, dirty experimentation to see which of these methods would be useful. That's the first step. And the next step, like I said, is really important. Define the requirements. So this is a cut down list of our requirements. There were many more, but this is kind of the main ones. So we need it to be real time. It needs to be low compute. It needed to be expandable and tunable. So we have different products, and different products have different sized processors on them. So some of them have like lots of power, some of them don't. So we wanted a solution where we could go, right, here's the MLDOA, I'll swap out this bit and put in a more powerful bit and it will still work. We wanted something that was kind of modular. They also have different microarrays, circular microarray. A lot of the meeting bars are linear microarray, and we don't want to write a completely different set of code for this. It needs to work for all of them. And then also we have different consumers for this. We've got the computer vision team wants to know who's speaking and when, so they can frame it. And they want an angle of arrival that's really stable, that's not going to jump around. They want to be really sure that they're going to frame that person that they are talking. Whereas the other avenue for this is the beam selection. So we steer a beam at a particular angle. And for that, we want it to move as fast as possible, because somebody could be talking over there, and somebody starts speaking over there, and you want it to immediately switch. We want it only to point to speech sources, so it needs to be robust to noise and reverberation. And also we made an assumption to simplify our life a little bit, which was we assume there's only one person talking at once. Of course, you can have multiple people talking over each other, but actually in a conference, a lot of the time that's a very short period of time. So we thought, let's simplify the problem and just assume that there's a single speaker at any moment in time. We can maybe modify and improve later if we can have multiple DOAs, but let's start with a single source. We chose, after our literature review and experimentation, we decided to adopt a hybrid ML approach. So when I say hybrid, it's part machine learning and it's part classical directional alignment. So it's based on the generalized cross correlation with phase transform. Who's heard of this? Yes. Okay. And this was based on a publication from somebody called Dillian Wang, who's well known in the speech area from Ohio State. And yeah, so it's based on this cross-correlation based analysis, which is looking at the time difference of arrival between microphones. That's kind of the basis of this. So the classical method, you're looking for, you've got two microphones here. You need to estimate what the time difference of arrival is, so that you can estimate what direction the wavefront came is it. And then you can compare that time difference of arrival with some knowledge of the geometry of the array, what you would expect it to be for a number of different angles. So you go, okay, I'd expect it to be no time difference of arrival if it's arriving straight on. Therefore, I know it's probably coming straight on. That's kind of the basic behind this method. It's hybrid in that what it has is that you can inject a speech enhancement mask into it. So you can basically use this speech enhancement mask, which is being trained to mask out reverberation and noise. So you can say, ignore these bins, these are from noise, just ignore them in this computation. Well, this was quite attractive because it means we've got some older products that are low power. We have a tiny speech enhancement model. It's like 50,000 parameters. It's really small. We can use that. We've got a new product which has got a great big processor in it. We can get a much bigger 2 million parameter model and stick it in, but we're using the same code. We've just swapped out a different model. So this was quite attractive, this method. We did find that if you can go for a fully ML solution, but you'd have to retrain your model for each microphone array. We felt it would be there'll be a tendency for it to be too sensitive, and we worried that we wouldn't be able to have the expandability that we have now. So the decision was to go for a system that perhaps isn't as accurate, but it lets us do all of this other stuff. Okay, I'll just quickly take you through how it works. So this is the GCC BAT transform. You've got two microphones, microphone P and Q, and these are spectra. So you've got spectrogram, short-term Fourier transform for some time frame, and you're comparing the two spectra from two different microphones. They're complex, and then underneath you're normalizing it by the product of the magnitudes. So this normalization basically means that we're actually only really looking at the phase difference between microphones. We don't care what the magnitude is. We're kind of throwing that information away. We're basically just looking at what the phase difference is between these two microphones.
Is that done per short-term Fourier block?
That's right, yeah. So, yes, every frame this is done. There's some averaging later on. Yeah. We then work out what the time delay would be between the two microphones for a whole bunch of candidate angles. So we make a plane wave assumption. We assume that we're in the far field, which as I talked about before, it's not the case because it's so far away. We assume the far field, and we then apply this relative transfer function between the inverse relative transfer function between that pair. So this is effectively attempting to undo the time delay that you would get. What this boils down to, basically, this function here is basically the phase difference between the two microphones. So this is the measured phase difference between the two microphones. And then what we have is the expected phase difference between the two microphones for a bunch of different candidate angles. So this is what this boils down to. Right. We apply a cosine to it, and the cosine makes this this function much more usable. So it avoids all phase unwrapping. If this is 0, you're looking for where this is 0. You're looking for where this phase difference matches this phase difference, and that's the candidate angle. And of course, if you take the cosine of 0, you get 1. So this makes it easy to maximize this function. So all we're doing is maximizing this. I'm always a big fan of a neat trick, and there's a neat trick here, which I really like. which is that this function here is just simply a complex number with an amplitude of 1, because we've got rid of all amplitude is just a complex number with an amplitude of 1, with a real and an imaginary part. And of course, you can represent the real part as the cosine of the phasor, and then the imaginary part as j times the sine of the phasor. So the neat trick is, you've just got some Fourier transforms, you've worked this out. You don't have to do a cosine. Cosines are expensive, especially kind of computing cosines. You don't have to do it because you've already got it. You just take the real part of that, and you've already got the cosine. And I like that. That's fun. Next up, we do an enormous summation. We've got this GCC coefficients here, and we sum over all frequencies. We sum over available time. So you have some past history of this. And then we sum over all microphone pairs. So you do this for different microphone pairs, sum everything up, and then find the maximum, or the argmax, and that tells you the angle. That's the algorithm. So I think you kind of agree it's fairly simple, but it's tried and tested. This is kind of works well. All right, there's been no mention of machine learning yet, so I should probably mention it right now, shouldn't I? How do we get the mask into this? So the way that this works is we compute, or the idea is you compute a mask on every microphone channel, and then for each microphone pair, you have a mask pair. You basically just combine the two. And what is a mask? Well, a mask is just it could be complex. You can have complex masks that apply to spectrograms to adjust the phase. I'm not worried about those kind of masks. We're just thinking about magnitude masks, where you're basically turning up or turning down different time frequency bins. That's all a mask is. So if you have a value of 1, it doesn't affect that time frequency bin. If you have a value of 0, it turns it off. So that's how a mask works, goes between 0 and 1. This GCC component, as I mentioned, this cosine, means this scales between -1 and 1. It's 1 where you've got a good correlation. It's 0 when you've got no correlation, and -1 when you've got inverted correlation. So they kind of function the same kind of way. You can just apply the mask directly to the GCC to turn off any time frequency bins and make sure they don't influence the choice. So if you've got some noise coming from some time frequency bins, you turn them off. And so in that summation, it no longer starts to select that particular angle. So that's how the mask works. Notice the I enjoyed that. And it's like, write me an image that says metrics are fun. I was like, one job.
Also, it's got like 3%. They're all just 3%, even though there's different.
Yeah. You know, the saddest thing is I didn't notice that. Slightly dyslexic. It's like there's something wrong about that word. I'm not sure. The next steps we call productionization. So this involves taking the prototype algorithm that we've created in Python and to start bending it so it's suitable for our needs, because it wasn't suitable from the outset. There needed to be a whole bunch of work to try and get it working in our products. The first thing we did was we set up a evaluation pipeline. So this pipeline is designed to take simulated audio recordings or real recordings which have been annotated, and then to produce some metrics about performance. We have lots of metrics, but the two that we used the most were gross accuracy. So this is what percentage of the predictions are within 5 degrees of the ground truth. And this one here was another one that we chose to use, which is transition from another direction. So you've got somebody talking at minus 30 degrees, somebody talking at 30 degrees. How quickly does the DOA switch from one to the other? So like I mentioned, for the audio beamforming, we want that to be super quick. For the camera framing, we don't care. We don't need it to be super quick. We just need it to be super reliable. So these metrics can help us steer the system. John pointed out before, you were asking, is this single frame or is it? Yeah, so that summation was basically summing over all time frames. So in the research, there was no accounting for real time. We needed to think about how do we look back in time over a certain period of time, and how do we sum over, how long do we look, how do we do this? And there was a lot of work spent on what we'll call heuristics. So these are basically, you can do a single prediction per frame. You could do no summing over time. You could sum over 50 milliseconds. You could sum over, a second or something. So there's been a lot of work trying to do this. We ended up with a system that basically an exponential weight into the past. We can tune it with and we can tune that exponential window to weight more of the past history or less of the past history, depending on the application. In addition, we needed to do more work to ensure that this could be deployed. We found that using all 512 bins independently was problematic, having to do those calculations every single time. So we found a way of compressing our representation, our phase representations in MEL. This is not something you would normally do. MEL is always magnitude. So we found a way to represent phase information in MEL bands, which was really rather reliable and doesn't offer very much reduction in performance. You go from fully linear or frequency bands to just 48 band MEL, or for our smaller products, 24 band MEL. And the other one is, if you remember, I said that we predict a mass from every single microphone channel. It's incredibly, that is the most expensive thing. You're doing inference on a big, a 2 million parameter model. That's the most expensive thing. You don't want to do that. So part of our work was we realized that you didn't need to do that. You only needed to select the middle one and predict the mass from that, as long as your microphone array is small enough, because then your sort of time delays, because we're not worried about phase for the mass. That's just sort of adjusting magnitudes. So as long as the expected time difference across the microphone array is much smaller than the frame, you're kind of okay. So we realized that we could just do prediction from a single channel, and that kind of made this possible. The last thing was we wanted a way to sort of automate this process. So we've got these two metrics, and it's always good in these kind of situations to define a single metric that you want to optimize, because then you end up, well, I've been in many meetings arguing about this metric or this metric. It's like if you all agree on one metric, then you can avoid arguments. That's my main motivation, just avoid conflict avoidance.
Metrics and devices.
Yes, metrics and devices. They're not, yeah, this is lies. No, metrics aren't. So we chose our optimizing metric. So this is the one that we want to maximize. We don't want to maximize anything else. We want to maximize this optimizing metric. So we want it to be as accurate as possible. But in order to tune our systems for different applications, we define what we call a satisficing metric as well. So this is basically a threshold on a metric. So basically in this, we define a maximum transition time. The transition time must be less than, I don't know what it was, I can't remember, but it must be less than 50 milliseconds or 100 milliseconds or something. Given that information, maximize the optimized metric with most accuracy. And that gives us our NLDOA for the beamformer, and then we can relax that condition for the camera. Yeah, and we have a Bayesian optimization framework that lets us do this. Next up, productionization. Sorry, production code. So this is I passed the Python code that I've written over to the embedded apps team, then ran away screaming. When they came back, they then implemented it in production-ready C++ code remarkably quickly. And I think having this embedded apps team embedded within our team is the secret sauce. This is the thing that lets us get out of the valley of death, mainly because they write the code, it runs on the product. The people with the purse strings then see it running on the product, and it makes for an easier decision to say, yeah, let's go do it. So I don't think all ML teams or AI teams have embedded apps embedded within them. And I would say that's kind of one of the secret sources for actually successfully delivering. They'll be pleased that I'm bigging them up. Once ported, we need to test it. So test. Integration was fairly easy because we already had a DOA, so most of the API was the same, so just put the new one in. So that can be difficult with new features, but for us it was fairly easy. Then testing it, running in the product, and there's a lot of feedback. It doesn't work in this situation, etc. Then I've got a quick video. There we go. This let me pause this. This is it playing? It's very quietly. This is basically one of the first tests that we did. So what we've got here is we've got somebody in a room talking in front of that Logitech site device, somebody on the remote end, but there's a speaker. The speaker's being projected out of it, and you'll see this is pointing to the person who's actively talking. Green means confident, red means not confident, and we're going to introduce a keyboard, another speaker here with a keyboard. This is kind of our first. This was our hello world. So. Can't hear anything. So that wasn't perfect because you may notice in the gap between speech, it did actually point there. So there has been improvements since that point out. But yeah, so the idea is it will during speech, it's quite reliable. It will point at the person who's talking, not the noise. So yeah, next stages would be to deploy it. So the MLDOA is now deployed in all of our products that are capable of running it. So that was quite an achievement. So I think we've made the correct decision about which algorithm to productionize. It's the simpler one. And we do get complaints, and we have a load of tools that we can use to diagnose and try and improve things. Last slide. So this brings me to the end. There are ongoing challenges. I just sort of note a few of them. One is head direction. So if you think about the frequency response of the sound is directional. So if I'm talking to you, you can hear all of my plosives and fricatives coming through nicely. But if I turn away in an anechoic chamber, I'm sure you've done this demo, that it's remarkably different. But if you think about it, what happens in a room that's got a glass wall, if you turn away from the device and you start talking, and actually the reflection sounds more like speech than your speech. So what can an MLDOA do? So that's a particular problem. Obviously, the only difference is time. You've got one reflection that's slightly earlier, but yeah, there's a problem with highly reflective surfaces. And then just the inherent limitations of linear arrays. So linear arrays, quite accurate in the middle, but nigh on useless at large angles. I mean, this is kind of the physical limitations, but we would like to push the boundaries of where it is accurate more and more out to the edges. Thanks.
Thank you very much, Paul, for a really interesting talk. Has anyone got any questions?
So early on, you said that there was limitations in data sets used. What are the specific legal issues at the end? Data sets that are on the face of it, they're out
Yeah.
there for people to use, but what stops you from using
So Will was just asking about what are the specific issues to do with why we can't use some data sets. And although I'm not the expert on this, the main issue is permissions. You need permission of the people whose voice it is. And of course, data captured by Google, they have none of that. Yeah, so we need sign off of the person whose voice that is. We're allowed to use that. So I think that's the main stumbling block, basically. Yeah.
Does it, if you've got a particularly like argumentative conference going on, how does it deal with that? I know it's like the active speaking.
This is a really good question. So we just had a question. It's about if there's a very dynamic case where lots of people are talking, what happens? So I would say that probably should be a limitation that I added there, because the assumption is a single person. So you picked up on that. So yeah, you do tend to get if it's not fast enough, it sounds a bit choppy. As it's switching between different people, it sounds a little bit choppy. It's not ideal. We are working on solutions for that very thing. This is kind of one of the active areas of research. It could be that we have direction of arrival, multiple simultaneous direction of arrival, and multiple simultaneous beams could be one solution, or it could be multi-mic is the solution, where everything's we move away from hybrid systems and let the machines take over a little bit. We give more spatial information to solve the problem, but it's a good point, because that is a particular issue where so John.
I was going to ask, do you use the face recognition information from the cameras to sort of guide potential directions?
We don't use it depends what you mean by face recognition. We do person detection, face detection. Recognition, no, we don't.
Detection,
yeah.
Just where is there a human?
Yeah, well, we don't, but the computer vision team have lots of algorithms that basically will actively be able to track a person's head direction and torso direction, and we are looking to using that information to try and improve our systems. For instance, some of our new products you want to use close up, no longer in the far field. We can know that, then we can adjust our algorithms accordingly to better do this.
the Mel phase thing? Is that an optimization that's particularly geared towards speech, or would that be applicable to other auditory events?
It works for anything, I think. I mean, it works well for speech because it's already segmented into kind of the salient bands. But it would work for anything. It's just it's basically just a decimation algorithm. Basically, just looks for what's the most important phase in a particular band and pick that. So,
awesome. You mentioned model size a few times. They seem quite small, some of the model sizes. What are the limitations of the devices?
Yeah. So Trevor's just asking about model size and limitations. I guess the model size isn't an explicit limit. It's kind of because of course it depends on what the layers are. But yeah, compared to some of the state-of-the-art models that are kind of doing, I guess that you're probably familiar with from Clarity project, are much bigger than sort of. So in particular, 50,000 parameters. It's amazingly small, and there's a particular challenge with getting systems to work that are so small, and it does an okay job. It doesn't do the great job when you've got stationary noise. Actually, problematic for stationary noise because maybe it doesn't have the frequency resolution to be able to separate out between the speech partials. But yeah, I mean,
does that come down to essentially cost? You're using cheaper chipsets to make it, because presumably larger model sizes are more possible if you just put the power into your devices.
Yeah, so I'm talking about older products.
Oh, okay.
So our newer products are capable of supporting larger models. but we are competing. So we're competing with the computer vision team who wants to use it for doing large models for speech, face detection, things like that. So we have NPUs, and so not everything's done on CPUs. Some things can be done off-boarded, and that's another thing that our embedded apps team, heroes, are working on to try and utilize these things so we can get bigger models. Yeah, a lot of work goes into model optimization. You train a model, but that's not the end of it. You then quantize the model. So you've got 32-bit float weights and biases. Try and adjust it to, if you can get it to into 8 floats and biases, then it's a massive saving. Of course, then the model doesn't work as well.
I have a question actually.
Yeah.
You said your ML DOA algorithm was improving on a DSP. Was that just regular old GCC fat, or was that something more exciting?
Actually, I don't know, because it was it's an external company that did it. So I am on the wiser. So we have contractors who do work for us as well. So that was yeah, that was before I joined. But, yeah.
Any other questions? No, in that case, thank you very much again.
Thanks for having me.